In this video, we're going to learn how to convert back and forth between Cartesian and polar coordinates. And where we're going to begin is with all of our transformation equations, or basically those currency exchange equations between Cartesian and polar. So let's just quickly remind ourselves what all of those relationships were. So if we want to go from xy into r and theta, what that meant was we had that r is equal to plus or minus the square root of x squared plus y squared. And we found that theta was equal to the arctangent of y over x. Again, that's because we're starting off with x and y, and we want to end up with r and theta. And the other equations we had were the opposite, going from r and theta. So we're starting off with a polar point, and then going into Cartesian x and y coordinates. And we found that x is equal to r cosine, and y is equal to r sine. And we found all four of these equations just by doing what we know about right triangles. Pythagorean theorem, and all of those trigonometric relationships. So in this video, let's go over actually converting points between polar and Cartesian, or Cartesian and polar. So the first thing we'll start off with is a point written in polar coordinates. So this is convert the point 2, pi over 3 to Cartesian coordinates. And just so we're on the same page, Cartesian, we again mean x and y. So this point we're starting with is a point written in polar coordinates where we're given our r and theta values. So we can just go ahead, pop up to the situation that we have up above and figure out which side we're on. And since we're starting off with an r and theta and we want to end up with an x and y, we're sitting on the right-hand side of these transformation equations. So we can just go ahead and plug in what we have. We're told that in this case, r is equal to 2, and we're told that theta is equal to pi over 3. So we have x is equal to r times the cosine of theta. So we just have to plug in those values. So we have r is equal to 2, and then theta is equal to pi over 3. Which at the end of the day, this is equal to 2 times 1/2, or just 1. We can do a similar thing for y. Y is equal to r sine theta. R again is equal to 2. And we're told that theta originally is equal to pi over 3. So our y value is 2 times the square root of 3 over 2, or just square root of 3. So what I always do actually with these problems is I usually make a sketch of just the point to make sure that we're ending up in the right xy versus where we're starting with the right r and theta. So for example, on the xy plane, we're starting off with the point 2, so we're a distance of 2 away from the origin at an angle of pi over 3. So first, let's compute that angle of pi over 3. So that angle of pi over 3 is somewhere along here. And then we're a distance about 2 starting from the origin. Okay, So now if we go out and change this to xy coordinates, what that means is, well, for x and y, we march off a distance of 1, and we would march up a distance of root 3. And it seems as though we're landing at the correct point. Of course, you could be a little more rigorous, but at least we're in the right coordinate, or the right quadrant of the xy plane. And the other subtle thing that we haven't explicitly mentioned so far is that polar points and polar curves, for that matter, live on the xy plane. So whenever we're dealing with a polar point, or point in polar coordinates, or a polar curve, which we haven't explicitly dove into yet, these always exist on the xy plane. So similar for parametric equations, where for sketching a parametric curve, we're sketching that parametric curve on the xy plane. All right, let's do another example. And on this example, let's do the opposite. Let's convert the point -1, 1 in Cartesian coordinates to polar coordinates. So again, we're starting off with Cartesian, so that means xy, and we want to go to polar, which is our r theta. So we're going to be on the opposite side of those transformation equations now, where we're beginning with an x and y, and we're ending with an r and theta. So if you remember those equations, we had that r is equal to plus or minus the square root of x squared plus y squared. So let's just plug in what we know for x and y. So we have plus or minus the square root. Let's make x blue, and let's make y red. So plugging in -1 for x, square it, plus 1 for y, and square it. And this comes out to plus or minus the square root of 2. All right, now that we have our polar distance, or polar radius, we can figure out what theta is. Theta is equal to the arctangent, or inverse tangent, of y over x. In that case, or in this case, what that means is it's equal to 1 over -1. Or in other words, this is equal to the arctangent of -1. Oops, which I forgot to write the minus. And if you're really good with your trig, well, we get two angles for this. We get the angles 3 pi over 4 and 7 pi over 4. So, at this junction, going from Cartesian to polar, it's a little more ambiguous right now, because we do have this plus or minus root 2, and we do have two different angles. So what are the actual polar coordinates of this point? Well, before we do anything else, let's just go ahead and make a sketch. So again, this is the xy plane. The point in which we're starting with is x equals -1 and y equals 1. So the point in which we're starting with is over in the second quadrant. So this is -1, 1 in Cartesian coordinates. So what we need then is, to say one choice, is if we have, let's say, r equals square root of 2, we need an angle to point us into that second quadrant. And well, if we're taking the positive square root of 2, we need that 3 pi over 4 angle to land us into that second quadrant. So we can do this combination of r equals square root of 2 and theta equals 3 pi over 4. Again, because we know that, well, we're a positive distance from the origin, and we're an angle of 3 pi over 4, that'll place us into the second quadrant. But now the question is, what do we do with that other point? Namely, what do we do with that negative square root of 2? And what do we do with this 7 pi over 4? Well, let's check it out. So just sketching again, the xy plane, our original point in Cartesian coordinates, that was minus 1, 1. Well, where does this angle of 7 pi over 4 put us? Well, an angle of 7 pi over 4, this would be pi over 2, this would be pi, and just keep going until we get to an angle. This would be the angle 7 pi over 4. It basically puts us down somewhere towards the quadrant 4. We want to land in quadrant 2. And well, here's the unique thing that we haven't mentioned at all. And the unique thing is, when r is negative, we reflect over the origin. And what that means is we add pi radians to the angle. So in this case, if we do have this angle that's shooting us into quadrant 4, the angle 7 pi over 4, but we want to land in quadrant 2, well, if we just use a negative value of r, that'll take us from here and basically shoot us over to the point that we want. So if we have r equals minus root 2, we can choose the angle, (7 pi over 4), and that combination will also place us at the correct coordinate. So just to summarize, when we do this conversion of Cartesian to polar coordinates, we actually end up with two different options for the coordinate representation in polar coordinates. The first case we started with, we ended up with the coordinate in r and theta that was square root of 2 and 3 pi over 4. So that was one plausible combination of r and thetas to land us at that point in the second quadrant. And the other combination we ended up with was, well, if r is negative, we can choose negative square root of 2, and we can choose 7 pi over 4, since that negative value of r is going to reflect us over the origin into the correct quadrant. So again, even though 7 pi over 4 would land us normally in the quadrant 4, because r is negative, it pops us over to quadrant 2, we effectively add pi radians to that angle.